Welcome back. Last video was about capacitance of interconnect, and in this video I will explain the resistance. Simple concept, not too much to cover here. There are a couple of key points that I really want to mention. So I think this is going to be a short video and I don't have to speed up that much. Sorry if I was too fast or too quick in the last video. Really, I always want to finish these videos within 15-20 minutes. My own attention time is about 20 minutes. After 20 minutes, when I listen to a presentation or watch a video, I start losing my concentration. So using that I use as a rule for myself to create that type of videos. By the way, those are recorded videos. If you get bored, you can stop it and always watch them again. And if you miss something, I don't write everything. Sometimes I talk a lot. So feel free to watch those videos or listen to these videos again. And hopefully things are clear. And anytime something is not clear, send me a text on LinkedIn. Thank you so much. Okay, resistance. Here is our metal. This is the weight, this is height or thickness. Sometimes I use height, sometimes I use thickness. Apology for that. Then the length, it doesn't stop here, it keeps going. That's what I'm indicating there. And you can see that aspect ratio that we have. And I explained that why metals are like that. Here is the formula. Again, as always, remember what you change and what impact on resistance happens. So this thing here is the resistivity symbol. Just like in capacitance, that's the permittivity. This is the based on the type of material. You don't need to get scared when you see these things. This just indicates, okay, for aluminum it will be one thing, for copper it will be one thing, for gold it will be another thing, and the resistance will be different for the same length and area. And for different material, this is going to make the difference. Okay, so this is a constant for a particular material. Then length over area, which means higher the area, more more width and height, less is the resistance. That's why we're not shrinking, we're not making an ideal square. We're trying to get as much as we can, and we typically try to go on the vertical side because our transistor guy is very small there. And we want to pack more and more wires in a smaller area. And if we make them bigger, transistor is scaling, and if interconnect doesn't scale, then our overall die size will not scale. Length, pretty reasonable, okay. More the length, more resistance. Simple, right? Few things I want to mention here. You don't need to memorize this, but I'm trying to make a point here. This resistivity is measured in ohm meter. How much is resistance like in a meter? Think like that. So copper 1.7. This number is constant, so I will just say this. Gold 2.2. Aluminium 2.7. Now if you look at my metal interconnect where I talk about the physical infrastructure or physical structure of the metals, I mentioned that in 0.25 micron aluminium was used. You must be wondering, if copper is a lot less, why we even use aluminium? Fair question. In the latest technology nodes, most of the things will be in copper. Aluminium has a little bit history. It was a low cost, and a lot of fabrication in those nodes was already kind of tuned for aluminium, for that material and use. It's also a better during the different etching or removing and all that type of different things during the fabrication. So just need to remember, aluminium at that technology nodes was a, people don't want to make too many changes. And if aluminium with the resistance, they can meet certain frequency and all that, they wanted to stay with that. They didn't want to make new changes and then risk of new troubles, new issues with the new change. So that time they were okay, but later on, as the technologies went down, eventually copper became the main guy. Some of the problems at that time they seen was copper can diffuse into other metals. or other materials. So that's why they stick with that. Yeah, and yeah, definitely. You have seen that in one of the videos. I mentioned that, okay, we can add titanium to aluminium alloy. So metals in 0.25 micron that I mentioned, they are aluminium alloy. Mean they use mainly aluminium. They use a little bit of copper, and then we also use some mix the titanium with it to reduce the um, resistance further, and or to improve some of the characteristics of copper, like it's diffusing into metals and all that. So there can we can add some barrier layers. Okay, that's it. That's enough for this one. Just remember that. You might be thinking, why are we not using this one? Okay, a continuity of this equation. There's a concept sheet resistance, and that is used in technology papers, and it will be there in different technology files that you look at. So I thought I also show that one. Otherwise, for basic resistance, that's a good concept, or that's enough concept. But if you look at for a given material or a given technology, so your material is fixed, aluminum alloy, fixed, and the height of the metals are also fixed for the particular technology, as I showed you here. Okay, different metals, their height has to be drawn like that. You can change the width or spacing between them, but height is fixed. So if this is a fixed constant, this is a constant, let's take them out and replace them with another constant, or the square is called sheet resistance. There's another way of measuring different metals on a technology. It's like a square of that metal um, in that technology node. Sorry. So I took some numbers. I'm trying to make a point here, not just for the sake of showing these numbers. This that I took from, actually some of these formulas I use from this very good book, Digital Integrated Circuits, by John Rabai and a couple of other authors here. So really good book. I used that during my master's degree, and I always keep that as a reference. It can go on sometime in too much details, which as a digital IC designer, especially physical design engineer, you don't need it, but still good to get the core concept. What I have seen in my career, that I spent 20 years in physical design. Once you start doing a physical design, then project after project after project, you're busy synthesizing, placing, routing, timing convergence, DRC, and all those things. Project after project, project after. And very soon you forget some of those core um, electronic concept, I would say, also transistor concepts and interconnect concept. And that's where things start getting boring. I mean, when we are in a bachelor or master, we are studying all this and it looks so much fun and all that. But once you are in a physical design or other RTL design, simulation, and all that, you are going more and more in a particular area. And some of those concepts you start forgetting, and it's not that much fun anymore. So knowing some of these things, it helps you. For example, if you read a technology paper on latest technology by Intel, by TSMC, and all that, then some of these things are important to understand. Okay, why they are changing the material for certain metals, why they are, why currents are increasing. You will understand some of the background of it. That will make it a lot more interesting. Okay. That's all. So what I wanted to make a point here was, okay, these are the sheet resistance for 0.25 micron from this book for a couple of layers. You must be wondering, when I drew that picture where the transistor was at the bottom and then you have different metals, you must be thinking of why we need metals. Why can't we just connect diffusions from one A to another one? Why just don't connect polysilicon, the gate material, direct to different gates as opposed to going to metal 1, metal 2? But look at these numbers. Diffusion is sheet resistance, for a similar kind of dimension is 1000 to 1500. Okay, so it's not a good material to make a long routes. It will have a lot of resistance. But what you have also seen, I gave some example previously where there was silicides put, those black things were put on top of the polysilicon and the diffusion area. And look at that, when you add that, then N plus P plus kind of become 3 to 5. So that's what they are used as a contact when you connect with another metal. You cannot just take it along because that is on the top side of it. So it creates a low resistance path when you connect to metal 1, for example. Similarly, polysilicon on its own 150 to 200, but when you add a silicide, it's 4 to 5. By the way, in comparison, aluminium, which is higher resistance than copper, 0.05 to zero point 0.1. Look, compare that number to these numbers. You will understand why we want to go into metal. I think that's all on resistance. I think that's enough. Yep. Yeah, in the next video, I will go over now. I will combine resistance and capacitance for an interconnect and build into some sort of delay modeling. And that will be the last video on interconnect. Thank you so much. See you next time.